In this video, we'll look at several things relating to graphs of functions. So this is section 1.2, analyzing graphs of functions. Okay, so the first thing that we're going to look at is something that we've already talked about in the last section, the domain and the range. And in the last section we defined these sort of algebraically and abstractly, but what we want to do this time is look at how can we tell what the domain and range are from a graph, and how do those relate together. We'll also revisit the vertical line test. For determining whether or not a graph comes from a function or not. And then the last thing that we'll talk about are zeros of functions and what they mean algebraically and what they mean graphically. So the first example we'll look at is I'm going to draw a graph of a function, and I'm not actually going to tell you what equation generates this function. It's actually not important for what we're going to do right now. So I'll graph the equation here, or excuse me, graph the equation, my secret equation here in red, and then I also want to put arrows at either end to indicate that the graph keeps going up in both directions. Okay, so the question we have here is, what is the domain? So this red graph is graph of mystery function f of x, and I'm not going to tell you what it is. Okay, so what is the domain of the function f, and what is the range of the function f? Just based on what the graph looks like, what can we determine? So the domain, we'll start there. What values of x are permissible to plug into the function is the algebraic question. From the graph, what we're asking is, if you pick some number x, so here's one right here, does the graph of the function appear somewhere up above it or below it? And if so, that means it's okay for this number to be plugged into the function. Now, what number do you get out as an answer? It's whatever the y value is of the red point, and it'll have to be somewhere above or below the point on the x-axis you choose. So, for the domain, we're asking which numbers on the x-axis do work for the function and which ones don't. From this graph, it looks like every number on the x-axis is okay to plug in, and this is why I went ahead and drew the arrows here, so that way over here we can imagine that the graph is way above and off the screen, but it still keeps going. So from the graph, it looks like that every x value is okay to plug in to the function. Okay, so the domain is the set of all, let's try spelling correctly, all of the real numbers. And we have a special symbol for that. It's an R with sort of this extra vertical line. So this symbol is shorthand for the set of all real numbers. Okay, now what about the range? It's sort of the same idea. If you pick a number on the y-axis, you want to see, does the function ever achieve that as a y value? And so you're asking, does the function ever cross this level? Now, in the range, it's okay for it to do that more than once. So, for example, here, the y-axis, or excuse me, the y value of this point and the y value of this point are the same as the one that we chose. So it's okay if it happens more than once here. So we need to ask that question basically for every single y value on the y-axis. And from the graph we can sort of guess that it's okay, or we're okay, as long as we ask about positive numbers or perhaps 0 because of it touches the axis right there. But if I choose this number down here, say, something negative, the graph, the red graph, doesn't ever hit that y value. Okay? So in this case, it's all non-negative, let's try this again, all non-negative numbers. That's how we'd say it in English. And then the symbols that we'll use this time would be, we need all the stuff that's bigger than or equal to 0. So I'm going to use square brackets because 0 is included in this set, a comma, and then this keeps going all the way to plus infinity. Okay, so that's my range. All right, so let's look at another example. And this one's a little bit more exotic. So we'll get here a set of coordinate axes. And then I'll draw this one in blue just for something different. So this one is going to go like this, and then like this, and we'll have an open hole here at both ends of this line segment. Okay, so let's call this mystery coordinate A, just to give it a name. Okay, so and so this is some new function, let's say g of x, and the domain, similar to what we did before, what x values look like don't have anything blue above or below them? All of the stuff over here looks good because we got this straight line there. All of the stuff over here, probably good because we got the blue line up above it. So the potential problem point is the stuff going on here right at x equals a, wherever this actually is. Now, here's where the open circles make a difference. The open circles mean that the function never actually gets to this point. It gets as close as possible to it, but without reaching it. So there is no blue solid stuff above the point A. So it looks like everything is okay except for the number A. So our domain is as a set, the set of x's, so that x is not equal to this number A, whatever its numerical value actually is. And now we can write that in several ways. Here I've written it in set notation. We can also write it as an interval. So the stuff not equal to A is either smaller than A or it's bigger than A. And the two things together are the things not equal to A. So I could write this with a comma. You may have seen the symbol before, just a sort of regular U called union, and that just means sort of both sets together have been combined, kind of like gluing them together. Okay, so that's the domain of this function. Now the range is a little bit more exciting here. Because looking at it, there are only 3 y values, or actually just 2, that ever get hit. This one and this one. Okay, so whatever those two numbers are, let's say that this is at negative, or at some number b, and this is at some height c. So our range are only the numbers b and c, whatever their actual numerical values are. So there's a couple ways to write a set where you just have, say, a couple things in it. One is just to put curly braces and list explicitly the things that are inside of it. If you've got just a few things, this is a pretty convenient way to do it. Now, something like our domain here, it's very inconvenient to try and list an infinite number of things, but we don't have that problem here. Okay, so just 2 things are in this range, the number b and the number c, whatever numerically they are. Okay. Okay, so now we're going to look at one more example of something that has to do with graphing. Um, but instead of talking about the domain and range, we're going to be interested in what information about the function, its actual numerical values, we can get out. Okay, so the first thing I'm going to do is just sort of draw the graph I'm going to work with, and we'll use, say, this purple this time. And I'm going to have to freehand this one, so apologies if it's not particularly beautiful. Okay, so here is my graph. And then I need to put some actual numerical markings on here. So this point here we'll say is at 4. And then we've got 2 here, 3, 1. And then let's say that this point over here is at, it looks like about 2. And then this point over here looks like it's at about -2. Okay, so that gets me somewhat of a labeling of my axes, and this is sort of roughly what the function looks like. Okay, so given this, what we want to know is what, roughly speaking, can we guess is an approximate value of something like f of 1, okay, based on the graph. Okay, now looking at it, so 1 would be about here on the x-axis, and where is the purple that's above that point? Looks like it's about here. So this point has x-coordinate 1, that's the input, and its y-coordinate looks to be about 2, so that's our output. So we should guess, based on the graph, that f of 1 equals 2. Okay, so remember, basically what we've done here is f of the x-coordinate should equal the y-coordinate. And all we have to do is find, for the given x-coordinate, what point on the graph, if any, has that x-coordinate, and then figure out, for that point, what's the y-coordinate. And that's where the axis labeling comes in. Okay, so let's pick another point here. Let's say that we're also interested in f of, oh, I don't know, let's say f of 3. Okay, so I'm going to come over here and put this in blue. So 3 is about there, and the point that's above it is, roughly speaking, there. So, you know, my art hasn't been exact here, so let's draw sort of a horizontal line over to the axis. And, well, maybe that's about 1 3/4 or 1 2/3, something in that sort of ballpark. Now, normally when you do this, you have graphs that are much better than what I've drawn here. But we just kind of want to visually estimate about what's the y-coordinate of this thing. If we ever want to do things exactly, we'll actually try and plug f of 1 into the function and do things, work things out exactly. But if we just want to get sort of a rough idea as to what's going on from a graph, this is usually good enough. Okay, so just based on eyeballing it, we said it's probably going to be about 1 3/4 or so. Okay, so 1 3/4-ish, close enough for government work. And that's basically the idea here. If we pick another x-coordinate, we just do the same thing. So the warm-up exercise that you'll do, you'll actually do this for 4 different x values, and I promise you the graph will be a little bit nicer than the hideous one that I've drawn here. Okay, so the last example that we'll look at is just what does it mean to talk about a zero of a function? Okay, so this is zeros of functions. Okay, so algebraically, the definition is the zeros are the things that make a function equal to, and that should be an equal to here, a function equal to 0. Hence the name zeros. Okay, now algebraically, we can do this by just solving the given equation. Geometrically, what we're asking is where does the function cross the x-axis? Now, it may not happen anywhere, but if it does, those places are called a 0. Okay, so if we've got, say, a nice little set of coordinate axes here, and we ask, okay, where, if ever, does this graph cross the x-axis, then it would be at these points here. So that one is a 0, this one is a 0, and that one is a 0. Now, from a graph, you can visually estimate the locations of these things, much in the way that we visually estimated points on the graph, other points on the graph in a previous example. But if you want to find these things algebraically, then you have to get your hands dirty. So for that, let's look at an example. So let's say that our function is something like 8x squared plus 50x minus 42. Okay, so we want to find the zeros of this thing. So all we have to do is set f of x equal to 0. So here's f of x, the given function, and I'm going to set that equal to 0. Now, if you notice, we've solved equations like this quite a bit so far. This is a quadratic equation, and so we can solve it using the same techniques that we would otherwise. Now, two things that I noticed that are a little annoying. One, we've got some pretty big numbers here, 8, 50, 42, but they're all even numbers. So the first thing I'm going to do is factor a 2 out, and hopefully this will keep the arithmetic a little bit easier. So plus 25 minus 21, and that equals 0. Now, since it's all equaling 0, I can divide both sides by the 2, and what I really have to worry about is just when the insides is equal to 0, not when everything else is. Not when the 2 equals 0, because that never happens. So we can just sort of work with this simplified, slightly smaller set of numbers from the other one. Okay, so if we just do the 4x squared plus 25x, and there should be an x right there, minus 21 equals 0, then all we need to use is the quadratic formula. I would not try and factor this because of the ugly numbers, and completing the square is probably not the best way to approach this one, so we'll just try the quadratic formula and hope for the best. Okay, so x equals negative b plus minus square root of b squared, so 25 squared minus 4 times a, which happens also to be 4, times c, which is negative 21. And that negative is going to be important in a minute. And then this whole thing is divided by 8, which is twice a. Okay, so then we've got some arithmetic to do. 25 plus minus 25 squared is 625. I just happen to remember that. And then this other one here, we've got 16 times 21. And so I'm going to cheat real quick and compute that. Oops, 16 times 21 is 336. Okay, so we've got minus, actually plus, because we've got a double negatives, plus 336. And then I want to add that to the 625, so we'll do 625 plus 336, and that gets us a total inside the square root of 961. Okay, so we'll write that in just a second. All right, so this is equal to negative 25 plus minus square root of 961 all over 8. And then let's see if 961 happens to have a nice square root, kind of a big number. Maybe we'll get lucky, and we do. That's nice. So it turns out that the square root of 961 is 31. So we have all over 8, and negative 25 minus 31 is going to be negative 56 over 8. Or if we add instead, we'll get positive 6 over 8. And then if we can just cancel these fractions, so 56 over 8 is going to be negative 7. Or we'll say just go ahead and reduce this one in 2. That's supposed to be a 4, 3/4. Okay, so there we go. Quadratic equations have, generally speaking, 2 zeros. They can't have any more than 2, but it is possible for them to have less than 2, and we'll talk about that more later.